Hey guys, in this video, I'm going to show you how to plot a particle size distribution curve using a semi-log graph paper. And also, I'm going to show you how to find the values of coefficient of curvature and coefficient of uniformity from the graph. Thereafter, I'm going to show you how to interpret the values of coefficient of curvature and coefficient of uniformity. So without further ado, let's get started. So as you can see, this is the sieve test tabulation, that is the sieve test calculation. I've already done the calculation for the percent wear retained, cumulative wear retained, and the cumulative passing. Let me zoom in a little bit. So if you don't know how to do the sieve test calculation or how to calculate the percent wear retained, the cumulative wear retained, and the cumulative passing, just click to the link in the description box. I've already done a video on how to do the sieve test calculation. Please, before I continue, support this channel by hitting the like button so that this will help the algorithm to share my video to more people. And also, if you have not subscribed to my channel, please subscribe to my channel for more videos like this. So now we're going to plot the sieve size in millimeters against the cumulative passing. So the sieve size is going to be on the x-axis, while the cumulative passing is going to be on the y-axis. Now let's represent the values on the graph. So here is our two-cycle similar graph. Now we're going to represent the values. As you can see from the sieve test calculation, we have the minimum value for the x-axis, the minimum value is 0.3, while the highest value is 2.8. So we have 2.8. So that means our value for the x-axis is going to range from 0.1 to 10, because this range of value 0.3 to 2.8 falls between 0.1 and 10. So, and also along the y-axis we have the minimum value as 0 and the highest value is 100. So that means we're gonna have so we have 0 and 100. So the value is gonna range from 0 to 100 on the y-axis. So now let's represent the values on the graph paper. It's going to be the sieve size. Sieve size in millimeters. Y, the y-axis is going to be the cumulative passing. In some textbooks, they usually use the term percent final. So whether you use the term percent final or cumulative passing, it's the same thing. So we're going to use cumulative passing. In percent. So now we're going to start from here, which is 0, here is going to be 10, 20, 30. So as you can see, it's increasing by 10 as you move, in this direction along the y-axis. It's gonna be 40, 50, 60, 70, 80, 90. Then lastly, we have 100. We can, write the rest. It's gonna be 110, 120, 130, 140, and so on and so forth. So, but our values is going to range between 0 to 100. So this is the most important, part of the graph. So now for the x-axis, we have from here. So the first value here, remember we said that the value is going to range from 0.1 to 10, because 0.3, which is the minimum value, and 2.8, which is the highest value, falls within 0.1 to 10. So this is the first cycle from here to here. The first cycle is 10 raised to the power negative 1. So 10 raised to the power negative 1 is 1 over 10, which is 0.1. So that means each of these subdivision is going to increase by 0.1. So we have here is going to be 0.1. So the first cycle, which is here, is, so the second cycle is 10 raised to the power 0. That's from here to here. So that means it's going to increase by 1 as you move in this direction. So here is going to be 1. So if here is 1, here is going to be 10, because 10 raised to the power 0 is going to give us 1. So here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here is going to be 10. So here is 0.1. In between, that's in between the subdivisions. In the first cycle, we have 0.1 here, and then here is going to be 0.2. Here's going to be 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. Then here is 1, because after 0.9 we have 1. So while here is 2 for the second cycle, because it's increasing by 1. So here is 1, here is going to be 2, it's going to be 3, 4, 5, 6, 7, 8, 9, and here is 10. So now that we have represented values on the graph, now let's plot the values. 2.8, 2.8 against 100. So as you can see, we have here is 1. So this is 1. So 2.8 is going to be somewhere in between here and here, that is 1, 2, 3. So between 2 and 3 we have 2.8. So the subdivision here is going to increase by 0.1. So as you move in this direction, so we have 2.1 here, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, and then 2.8. So this is 2.8. So let me place this ruler here in order to help us to locate the line. So 2.8 against 100. So this is 100 on the y-axis. So this is where we're going to plot the point. Next, we have 2.0 for the x-axis against 90.91 for the y-axis. So 2.0 against 90.91. 2.0 against 90.91. So we have 2.0 is going to be here, because here is 1, so here is 2. So we have 2 for the x-axis, and then 90.91 for the y-axis. So 90 is here, so let's place the ruler here. So 90 is here. So 90.91 is going to be between here and here, because after here we have 92, 94, 96, 98, and then 100. So it's increasing by 2. So between 90 and 92 we have 90.91. So we're gonna plot it here. Next, we're gonna plot x-axis 1.40 against y-axis 71.17. So 1.40 against 71.17. X-axis 1.40. So here is 1, 1.1, 1.2, 1.3, 1.4. So 1.4 is going to be here. So 1.4 against 71.17 on the y-axis. So let's place the ruler here along the 1.40. Now let's find the 71.17. So between 70 and 72, that's between here and here, we're going to have the 71.17. So So 1.17 is going to be somewhere right here. Next, let's plot the values for 1.0 against 45.72. 1.0 x-axis against 45.72. So we have 1.0, which is here, against 45.72. Here is 40, 42, 40. Here's going to be 44. So 45 is going to be between 44 and 46. So somewhere around here. So have 40, 42, 44, then 45.72 is going to be somewhere here. The next, we're going to plot 0.71 against 24.94. So 0.71 for the x-axis. So 0.71 is going to be somewhere around here. We have 0.1 here, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 is here. So 0.7 when it's going to be somewhere here, because between 0.7 and 0.8 we have 0.75. So 0.71 is going to be somewhere here, and then against 24.94 on the y axis. So 24.94. So here we have 20, 20, 22. Here is 24. So 24.94 is going to be somewhere around here. So the point is going to be here. Next, we're going to plot 0.5 x-axis against 11.95. 0.5. So here is 0.5. This is 0.5, 0.1, 0.2, 0.3, 0.4, 0.5. So 0.5 against 11.95. So 11.95 is going to be somewhere here. We have 10 here, and then the next value here is going to be 12. So between 12 and 10 we have 11.95. So this is very close to 12. So it's going to be somewhere here. So lastly, we have 0.3 against 3.12. So 0.3 on the x-axis. This is 0.3, as you can see, against 3.12 on the y-axis. So here is 0, here is going to be 2, and then here is going to be 4. So between 4 and 2 we have 3.12. So somewhere here, 3.12. So now we are done plotting the data on the graph. Now the next thing is we're going to draw the curve. So let's draw the curve. I'm going to use this flexible broom to draw the curve. As you can see, now I've drawn the curve using this stick. This is a flexible stick, so this is very helpful in order to get a smooth curve. But if you can do it by hand, there's no need to use this stick. So now that we have drawn the curve, we are going to find the values for the coefficient of curvature and the coefficient of uniformity from the graph. So in order to do that, we're going to first find the value for D10, where you have the 10% for the cumulative passing. That's the value for D10. Where it intersects with the curve, and then we trace it down to the x-axis to get the values for D10. So this is 10 for the y-axis. So we're going to trace it until it intersects with the curve. So we have the line here horizontally. So as you can see, this is where it meets the curve. So we're going to trace it down. So this is the D10 value. So the D10 value, as you can see on the graph, is going to be, here is 0.4, here is going to be 0.42, 0.44, and then we're going to have 0.45. So we have D10 equals 0.45. Next, we're going to find the value for D30. Now, D30 is where you have the 30% for the cumulative passing along the y-axis. So this is 30%. We're going to trace it until it meets the curve. So where it intersects with the curve is the D30 value. So this is where it intersects with the curve. So let's trace it down. So we have D30 here. So as you can see, the D30 is between 0.75 and 0.8. Here we have 0.7. The next value is going to be in between 0.7 and 0.8 is 0.75. So in between 0.75 and 0.8 is 0.775. So approximately the value for D30 is 0.78. So lastly, we're going to find the value for D60. So as you can see, we have D60, the cumulative passing here, which is 60%. So let's stretch it to make a curve. Yeah, so this is where it meets the curve. Where it intersects the curve, we're going to trace it down to the x-axis. To get a value for D60. So this is where we have the D60 value. So as you can see, the D60 value is, between 1 and 2. So here is 1.1. Here is going to be 1.2. So approximately 1.2. So the value here is 1.2 for D60. So now that we have the value for D10, D30, and D60, we are going to calculate the coefficient of uniformity and the coefficient of curvature. The value for D10 is 0.45. D30 is 0.78. Then D60 is 1.2. Now, D10 is also known as the effective grain size. Now let's find the coefficient of curvature. The coefficient of curvature CC equals D30 square over D10 times D60. So the value for D30 is 0.78. Square. Value for D10 is 0.5. The value for D60 is 1.2. So using our calculator, let's so here we have 0.78 square. It's going to give us 0. So let me adjust this a bit so that you can see it very well. So we have 0.6084 over 0.45 times 1.2. We have 0.54. So if you divide 0.6084 by 0.54, we have 1.12. 1.12. So approximately CC is 1.13. So this is the value for the coefficient of curvature. So next we are going to find the value for coefficient of uniformity. CU. So the formula is d60 over d10. So the value for d60 is 1.2, while the value for d10 is 0.45. So if you divide it, we have 1.2 divided by 0.45. So the answer is Cu equals 2 point, approximately 2.7. So this is the coefficient of uniformity value. Now you might be wondering, what is the meaning, or what is the essence of calculating the values for CC and CU? Now, for construction purposes, I'm going to interpret and I'll show you how to interpret these values for construction purposes. Now, if you have CU, let me take this, move this a little bit here. So if you have CU greater than 4 and CC between 1 and 3, it is well graded. Well graded well graded soil. In this case, it is gravel, so that is when it is gravel. So this is for gravel. So if it meets this condition, that is when Cu is greater than 4 and Cc is between 1 and 3. If it meets this condition for a gravel, then it is well graded soil. But if it doesn't meet this condition, or if it doesn't fulfill this condition, then else it is poorly graded. Also, if Cu is greater than 6 and CC is between 1 and 3. For a sand is so that's for sand, it is well graded. That's for sand. But if it doesn't meet this condition, or if it doesn't fulfill this condition, then else it is poorly graded. So based on that, we have our value here for CC, which is 1.13. As you can see, 1.13 for CC falls between 1 and 3. So, and how about CU? The value for CU, well, the value for CU is less than 4. So it's not greater than 4. So it does not apply. So in this case, it's poorly graded. How about for sand? The value for CC is between 1 to 3. Yeah. How about CU? CU is 2.7, but it is supposed to be greater than 6. So it is not well graded. So it is poorly graded. So this is poorly graded sand. So it's if you are asked to classify this, the value for C, when you have the value for CU less than less than 4, so it is either uniformly graded, or so it is either uniformly graded or gap graded. So both uniformly graded and gap graded are classified as poorly graded. So that means in this case, our values, based on what we calculated for CC and CU, we have a poorly graded, sand. So in terms of construction purpose, well-graded soil is preferred because it has, lesser void ratio compared to, uniformly graded soil or gap graded soil.